In fact, if you could do it even slightly better than brute force, you would get dramatic consequences in complexity theory that are unknown. And this is a recurring phenomenon, where progress in randomization is inherently tied to progress in other areas of theoretical computer science. You know, just as an anecdote, I don't know how to do it in polynomial time, even if the circuit is a CNF. All right. So we don't know the answers to these, but there is a big and what I like to think of as a surprising conjecture, which is a classical one, which is that for a big chunk of computational problems, randomness doesn't help. And we're used to taking this conjecture for granted. It's been taken for granted, I think, since the 70s. This is basically the P versus BPP conjecture, the conjecture that P equals BPP, and it's a weird conjecture. Intuitively, it says that for all classical type of problems, decision problems and natural search problems, you don't gain a lot by using randomness.
Of the 70s, everybody conjectured the opposite.
No, in Gill in 1977, he conjectured that you can de-randomize in linear time.
What? Sorry?
Gill in 1977.
No, Gill, of course, his paper, he defined, but this was, you said everybody was taking it for granted. Nobody was taking
it for granted?
No, nobody.
Would you share? Because I got a different story from Oded and I want to know the story.
Well, no, in the late 80s, after cryptography, mid to late 80s, people started.
And in the 70s?
No.
Okay, so Gill is an outlier?
He's an outlier. He defined BPP, so
right.
He gets, maybe his vote counts more than...
when BPP was defined...
In fact, also in the 70s, there were extremely, or relatively few problems where randomness was, it accumulated in the 70s and 80s, lots and lots of new randomized algorithms. So popped up, and it strengthened the belief that it's different.
Okay, I really need a history lesson later.
Okay, yeah, that was a shock of it.
Right. Anyway, so Gill, which is an outlier, apparently, like when he defined BPP, he conjectured that you could randomize it in linear time without any overhead, which we believe today is impossible in some senses. But anyway, it is a surprising conjecture. Right? In textbooks, you take this conjecture as one of the big conjectures in complexity theory, but we just saw how crucial randomness is, and it's weird for such a big class not to benefit from using randomness. So let's define it formally. We will need a slight generalization of languages, which is called promise problems. So a promise problem pi is a pair of disjoint sets of strings, the yes instances and the no instances. You need to say yes on yes instances, and you need to say no on no instances, and I don't care what you do on everything else. Just the algorithm can blow up. I only care that it works well on either on yes instances and on no instances. Okay, and we define promise BP time t. So a promise problem pi is in promise BP time t. If there is a probabilistic t time algorithm A that gets an input x of n bits, runs in time t of n, and if x is a yes instance, then the probability that A spits out yes is high, and if x is a no instance, the probability that A spits out yes is low. And BPP is just BP time t for all polynomials t. And the conjecture that you know is that promise BPP equals promise P. Promise P is the analogous deterministic class. As a side comment, we're working with promise problems and not with languages because it gives nice structure for promise BPP. If we remove the promise, then we get into some technical difficulties. Any questions about this? All right, so as usual in complexity theory, we talk about decision problems, but we're actually talking about a larger class of natural problems. This is just a methodological simplification. So we want to say that if promise BPP equals promise P, just de-randomizing decision problems, we can also de-randomize all the relevant search problems. So let's just define this properly and state the result, just so that it will be clear. So this is a cumbersome definition, but it is the most natural. So take again these joint sets, yes instances and no instances. And these are the inputs, and we want to find solution given these inputs. Okay, so with every yes input, we associate a set of solution. So the yes input is x, and the set of solution is w sub x. These are the good solutions. For every no instance, the set of solutions is empty. For everything that is not a yes or a no instance, I don't care. And we consider the search problem in which the input is in the promise. It's either a yes instance or a no instance, and I need to output either a solution if X is a yes instance, or just say you are a liar, you are a cheater, there are no solutions if X is a no instance. And we say that such a problem is in BPP search if there are two conditions. We can solve it in BPP and we can recognize solutions when we see them. The first condition says that there exists a probabilistic polynomial time machine F for fine, that for yes instances, with high probability it spits out solutions. I don't care how it works for no instances because of the second condition. There exists a probabilistic polynomial machine D for the decision, such that when you give it X and when you give it W, it says yes, it decides whether or not W is a valid witness for X.
So the second condition generalizes the usual NP condition. You can test witnesses.
Exactly.
So if the problem was testing compositeness, then the set of witnesses are the factorization. So,
precisely. Yeah. Exactly. This is just a natural generalization of NP search problems to the setting of BPP. And the theorem is that if you can solve the decision problems, then you can solve these BPP search problems. So if promise BPP equals promise P, then every BPP search problem can be solved in deterministic polytime. There was a question? Oh, okay. But it is a good time for questions. Good. This captures most of the natural search problems that we can solve that you can think of. So the point here is that really the problem that we care about is a natural problem. It says that we can derandomize everything that is natural. Okay. Mimicking the situation in the research about P versus NP, the research in BPP versus P has two general areas. One area is unconditional results. Derandomizing specific problems. Try to find the problem. Try to construct an expander. Try to solve undirected connectivity in log space. Specific problems and solutions. And also derandomize weak classes of algorithms. Algorithms whose decision as a function of the random coins is a constant depth circuit. We can do that more or less, not in polynomial time, but we have results. This mimics in P versus NP the attempt to prove unconditional lower bounds. And the second area is to prove conditional structural results. Connect P versus BPP to other classes in complexity theory, find connections to other major problems, find sufficient and necessary hypotheses for randomization. And this is, for example, the area of hardness approximation currently, in every structural result in complexity that you know. Okay. So as Avi said, we will have a three-part talk series. It will focus on recent developments in derandomization from the last couple of years. I will speak today. Lijie Chen, who is visiting for a couple of weeks, will speak next week, and then I will speak again in 2 weeks. This talk will give an overview of like the area, what is known, what are the big open problems, and we'll show one technical result, which is something very recent called super fast derandomization. Derandomization with as little overhead as possible. Lijie next week will talk about the super exciting recent result, which is an unconditional, non-deterministic PRG. We will define this for a weak circuit class, for which we did not know such a thing. It's called ACC0. And then in the last talk, we will talk about two other recent things, which are called free lunch derandomization, randomization where you pay nothing, and non-black box randomization, which consists of new techniques. And I'm moving on unless there are any questions. I want to give the big picture of what is known in broad strokes. Classical approach for derandomization relied on something called pseudo-randomness, and in particular on PRGs, pseudo-random generators. So let's define this because we're going to need this. So we say that a function D and single bit epsilon distinguishes distribution W. This is the distribution over 0, 1 to n. Uniform if D behaves differently when it gets something from W and when it gets a uniform string. So if the probability that D spits out 1 from W is different than the probability. Yes, and you're right. And the PRG is something that spits out a distribution W that looks uniform to a set of potential distinguishers. We fix a set of potential distinguishers. So it's asymptotic. For every n, you have a set D sub n. It's a set of functions from 0, 1 to the n. 0, 1, and an epsilon PRG for this class D is an algorithm that takes as input 1 to the n and a random seed length L of n. This is the length. Intuitively, it stretches the random seed of length L of n, which is much smaller than n, to n bits that look random to any one phone. Such that no D in D sub n can epsilon distinguish the distribution G 1 to the n. This is uniform over the seed or uniform. I'm keeping this while I'm running. Find this theorem. The theorem is that if there is 1/10 PRG with sigma of n for circuits of linear size, then we get randomization. Promise BP time. Contained in B time. And I forgot to write something that I will add 2 to the L and to the T. I forgot to add that the running time is exponential in the signal.
Running time of the PRG.
The running time of the PRG. So if there's a PRG with seed length L and running time 2 to the L, or polynomial in that full circuits of linear size, then we get the randomization of time t in approximately deterministic time 2 to the L of t. And really, it seems easy. We're going to prove it in a couple of lines, but something weird snuck in the back door. Because I mentioned something circuits of linear size, which is weird. It's not clear why I'm talking about circuits at all. Okay, let's do the proof and see why we're talking about circuits.
Even before the proof, just set L of n to be about log n. That's a good parameter to look at, and then you get BPP equal. But if it's a generator which exponentially stretches the seed log n to n bits and has this property that it follows any linear size circuit, then BPP equals.
Right, good, and thank you. And just adding to what Avi said, by probabilistic method argument, there exist PRGs with seed length log n, but it's a non-explicit argument. We don't know how to compute them. We want to be able to compute them in exponential time. Okay, so let's do the proof and see where these weird circuits came in. So given a probabilistic t-time machine, input x, we construct the following circuits. Circuit C sub x gets random coins R and mimics the behavior of M on input X with random coins R. Now, if you look at C sub X of R, the number of input bits that it has is T. Its size is O tilde of t, and I'm going to ignore the tildes and everything here, and just by padding everything, you can assume that it's exactly t. So it's a circuit of linear size. So it is fooled by the PRG. And therefore, the behavior of the circuit on a random input is up to some small constant factor identical to the behavior of the circuit on a pseudo-random input from the output set of the PRG. And we can explicitly compute this thing, the probability that C accepts G by just enumerating over all the seeds, and it will tell us whether or not M tends to accept X or M tends to reject X. This is the entire proof.
So the terms there is related to the fact that this probabilistic machine either accepts with probability 2/3 or reject.
Right. So where did circuits come into the picture? Well, we just wanted to de-randomize this machine M. However, we wanted to de-randomize M on each and every possible input. So when we get M and the possible input X, we can think of X as sort of like a worst case non-uniform adversarial advice. Someone is trying to help M, giving it advice that will help it to distinguish the PRG. So when enumerating over all inputs, including worst case inputs, we get this class of circuits enumerating over all C sub X's. And this is why we get non-uniform circuits. Questions?
People who didn't see the distinction between uniform and non-uniform complexity is this, the assumption seems to be much stronger than what is needed. You want to full algorithm, but you assume that you have a hard function or a pseudo-random generator for circuits, which are non-uniform.
Precisely. And again, the reason why we had to do this is because we wanted to work in the worst case for every input. Okay, now I'm going to write something that will accompany us for the next half hour. This is going to be a very big table. We're now starting to survey results from the 90s. Like this. Oh, one other thing that I want to say about PRGs before moving forward. They don't only give us the randomization. A PRG gives us the randomization, but also in a specific way that we think of as a black box way. If you look at it, we can enumerate the seeds of the PRG and generate a pseudo-random set before we see M and before we see X. You can switch the order of quantifiers here. First, you instantiate the PRG, you enumerate the seed, you get all the pseudo-random strings, only then someone gives you M and gives you X and it works for them. So this is why we call it a black box way, because it doesn't even need to look at the circuit C sub X before we begin. So we're now talking about a worst case black box randomization.
You can write a little bigger.
Okay, yeah, I've tried to write a little bigger.
Line was big enough.
No, I need to put it lower. Worst case black box. Okay, and the randomization here is a PRG for circuits with seed length that is logarithmic. Overflowing. Whenever I omit the running time, it's exponential in the seed length. And a result of Avi and Russell in Pagliazzo from the late 90s, following a result of Avi and Noam Nissan from the late 80s, is that this is equivalent to lower bounds for circuits. So a PRG for circuits is equivalent to lower bounds for circuits, and I will say exactly which lower bounds. Exponential time. It's hard for something that I'm writing simply because I'm pedantic and you should ignore. I don't want to write wrong things, but forget about this. Circuits of size that is a smaller exponential. Say epsilon n for some epsilon. So the lower bound for circuits that is equivalent for PRGs is of the following form. We can compute in time to the n something that we cannot compute in time 2 to the epsilon n by non-uniform circuits.
So for example, possibly satisfiability. Okay.
No, wait, satisfiability, you can compute in time 2 to the n.
Okay, yeah.
Like in terms of input layer.
Yeah.
But I don't know, some incomplete language here that can be exponentially hard.
Yeah.
So if I would not write size here, I would write time, then the theorem would be unconditionally true. It's a time hierarchy. Larger time is hard for smaller time. But we are mixing resources. The smaller time also gets non-uniform advice. It's a class of circuits now. And if this holds when we mix the resources, larger time beats smaller size, then we get a PRG and vice versa. Right, this is Pagliazzo-Widerson 97. Okay, good. We have a final conclusive answer for this kind of PRGs. They're completely equivalent to this. But what if you don't believe this hypothesis? I find it hard to get intuition for circuits of exponential size. Okay, the result scales. So I'm going to be a bit informal in parameters. If you're only willing to assume that exponential time 2 to the poly n is hard for polynomial size, then you get an equivalence with PRGs that have a larger sigma. N to the epsilon, which gives you the randomization of BPP in time 2 to the n to the epsilon.
Sorry, what does this IO mean?
It means something that I really ask that you ignore.
Okay.
So this PRG means that we can derandomize in time 2 to the n to the epsilon, and this is a very believable hypothesis. It just says that with polynomial size circuits, you can't decide all of exponential time. And this is Babai, Fortnow, Nissan, and Widerson in 93. And you can cover the entire range in between, although it takes a lot of work. The final results are by Chantiel and Humans. And as a side note, if you assume standard cryptographic assumptions, you get this thing. Good.
It's much weaker than the cryptographic.
Which assumption did you think? I thought of one-way functions secure against non-uniform poly size.
Yeah, but you allow exponential time.
Oh, yeah.
You allow it.
Yeah, thanks. Yeah, right. As I said, this is much weaker. Crypto gives you this. If you don't believe in the randomization, you should, but you do believe the bottom row, you should stop believing somewhere in the middle as you go up. It's a weird situation. But okay, this gives us an answer for non-uniform PRGs. Oh, sorry, for PRGs against non-uniform. Where can we go from here? Can we weaken the hypothesis further? Well,
is the non-uniform result for SAT believed to be near optimal, the n over log n?
N over log n is like an unconditional algorithm in terms of the input length because in order to represent a formula over n bits, you need n times log n bits of input. But you can solve it in time 2 to the n, right?
Oh, I see.
So SAT isn't a good candidate for this exponential hardness, but it's a good candidate for like slightly below the exponential hardness.
There are ways to encode SAT.
Yeah, succinct SAT.
Yeah, it's the obvious way. Those are the log n.
Right.
Anyway, there are plenty of algorithms, plenty of problems that require exponential time that probably are hard.
Okay. So what happens if we only get a PRG? Like we fooled non-uniform circuits because we wanted to work in the worst case. Now I want to say that we can fool uniform circuits and do the randomization on average, which is another strand of result from around this time period, slightly later. So let me define an epsilon PRG for uniform circuits satisfies the following. So we have a machine for every probabilistic algorithm. This is a machine that tries to print efficiently a circuit that distinguishes the PRG. Any input length, the probability that A succeeds in outputting the distinguisher is A prints epsilon distinguisher for the output distribution of G is a post epsilon. It's the natural generalization. It says that you cannot efficiently print the distinguisher. And I'm going to just need one more technical definition to state the result. So we want to define sampleable distributions. So we have a set of distributions, X, which is like asymptotic, X sub n, where X sub n is over 0, 1 to the n. We say that it's t times sampleable if there is a t time machine that outputs it. There exists a t time probabilistic algorithm such that the output distribution A and input 1 to the n when I give A random coins, it spits out a string that is identically distributed to X sub n. For example, the uniform distribution is, of course, linear time sampleable. You can think of other distributions. And you might also think of these distributions as someone trying to find a bad input.
Not linear exercises that the uniform distribution on times is efficiently sampled.
Exactly. Thank you.
Can you repeat the first definition there? Like just say the words again. There are two things I can't.
Oh, sorry. So an epsilon PRG for uniform circuits is an algorithm G. That satisfies the following. For every probabilistic, oh, I didn't write something. Thank you. Okay, so for every probabilistic linear time, it's for simplicity. So for every probabilistic linear time algorithm A and every sufficiently large input length, the probability that A, when given input length 1 to the n, manages to print an epsilon distinguisher for the output distribution of G on 1 to the n with a random seed is at most epsilon. So previously we had PRGs that worked against all possible circuits. Now we'll have PRGs that work against circuits that can be uniformly generated.
The second definition, when you say it outputs distribution, means if you give it a random string, it also has a.
So yeah, let me be.
Okay. It doesn't actually print the values, right? It just prints, if you give it a random string, it prints the. Okay.
Exactly. So just to parse this syntactically, this is a random variable or a distribution with a uniform random string here. And this distribution is identically distributed to this.
Yeah.
The notion of sampleable distributions has a long history. It's not was motivated before these issues of derandomization. Just trying to understand when can you solve problems on natural distributions. Like maybe naturally arising distribution, but when can you solve linear problems on various natural distributions? And Levin suggested this. I mean, sort of, you can really an NP-hard problems of them. This set of distributions, those are sampleable efficiently. You can imagine that nature is an efficient process. Maybe it generates weird inputs, but it doesn't efficiently. So if we could do that, probably we could solve all the problems we want. The machine learning.
What we're going to see here is the exact generalization or extension of what Avi said, that we are going to de-randomize on average. So with respect to a class of distribution, which will be this class. So if there exists an epsilon PRG for uniform circuits, has seed length L and runtime 2 to the L, then for every problem L in BP time T, there exists the de-randomized version L prime in D time 2 to the L. Okay, so this is the original problem, and this is the problem that de-randomizes L on average, such that for every T time sampleable X, the probability when taking an input X is different than L prime of X is at most epsilon. So the derandomization works on average with respect to a class of distributions, the class that are T times sampleable. And another way to look at it is to start from L and to say that we de-randomized it by L prime, such that every bad, annoying adversary that runs in time T doesn't manage to find an input on which the derandomization fails, except with probability epsilon. Let's try. Oh, good. This is very much.
Take L to be logarithmic. This would say that under this weaker assumption, you can de-randomize on average every probabilistic algorithm.
Exactly. Thank you. Okay. This is again a black box derandomization because we are using PRGs. And it only works on average. And what can we say here? Well, let's mimic the top row, but instead of proving an equivalence between lower bounds for circuits and PRGs for circuits, we're proving an equivalence between lower bounds for machines and PRGs for machines. So let's mimic the bottom row. We have an IO PRG, and we ignore the IO for uniform circuits, seed, and to epsilon. And this is equivalent to exponential time to the poly n or BTP. So again, was proved by Avi and Russell and Pagazzo in the late 90s. If you just parse the parameters, you get an exact mirroring here. Except that here we only have lower bounds for uniform machines, and we get an average case randomization in time 2 to the n to the epsilon. I'm seeing some confused faces, so I'm stopping for a moment.
Yeah, ask questions.
What about the analog of the Impagaso Victor set?
I will get to it in after the pause for questions. I want to allow more questions before saying, ah, great.
Is there any interaction of this definition with like Kolmogorov complexity? Because I'm thinking of a silly example where you completely ignore U and just use the time you have to write a single word.
There are many, many ways to instantiate PRGs using strings with that are hard in terms of Kolmogorov complexity for various notions of Kolmogorov.
I see.
Yeah, the classical notion doesn't mention time it takes, but you realize that, that you need also the time it takes, so not just the size of the machine it takes to print a string, but actually the time it takes. So people generalize the notion of Kolmogorov complexity to time-bounded Kolmogorov complexity, and then you can integrate it to it.
Right, I see, exactly. And also, like, if you want in the recess, we can do a toy example. If I give you a string that has maximal Kolmogorov complexity, it's easy to build a PRG. It's a toy example. You know what?
I'm not sure we're talking about the same thing, but we can take it offline, I guess.
Okay, so let's take it offline. But if I will get to it again, I will tell you again in the next half of the talk.
Okay.
It is curious that one of the first non-trivial results about BPP, namely that it is in the polynomial time hierarchy. Right? It's not an NP for any obvious, because it has two-sided errors. So it's not NP, but maybe it's in some, a little higher. The hierarchy is the result of Mike Sipser. In this paper, I mean, you don't need it, but in this paper, he introduced time-bound Kolmogorov complexity for this purpose. And then you can bypass it. But that's how, that's where it came up. Yeah, that's
the first definition of time-bound.
That's very fun. Yeah.
All right, good. So I want you to notice that this is an extremely weak hypothesis. The converse of this hypothesis says that BPP equals exponential time. Any problem that you can solve in exponential time, you can solve in polynomial time. This is not very believable, which means that you can reasonably believe that there is at least an average case sub-exponential time derandomization. How do we scale this up? Okay, the thing that I should write here is time 2 to the n, which is hard for BP time 2 to the epsilon n for some epsilon. And here I should write a PRG for uniform circuits with seed of log n. And this is what you wanted to ask about, right? Like this direction is easy, and the problem with this direction is that it is not known. This is an open problem. We know how to scale from here until slightly below, but we don't know how to get this. And this is a very active area of research. Like if you look at Foxtop papers, you will see papers like from recent years doing this. Like 2 years ago, we got almost up to here. And like the most recent result kind of works for this parameter setting if you replace exponential time with linear space, so it's the Springer requirement. And if you replace PRG with a heating set generator, which is something a bit weaker, that suffices for a weaker derandomization. But we don't know how to actually prove this. However, it's morally true. It should be true. We should be able to prove it at some point, okay?
But it at least hints that the bottom part is even harder to prove than the top part.
Exactly.
Results for uniform circuits. I mean, I guess you're not going to show anything about this proof, so it's.
No, I'm going to mention it.
You are,
Yeah.
Okay, good.
But yeah, exactly. Proving results here is harder than proving results over here. Forget about this gap for a second, okay? Pretend that we already proved it. Go 5 years into the future. We kind of have a complete picture here for PRGs. Okay, these are PRGs for circuits. They're equivalent to lower bounds for circuits. These are PRGs for machines. They're equivalent to lower bounds for machines, up to some gaps that I don't want to think about right now. And like whatever hardness assumption you throw in, you get the corresponding PRG. Moreover, this is from the 90s. Almost all of these, all the results that are written on the board are from the 90s, and like these scalings are not from the 90s, but fine. They are scalings of the basic principle that you know. The big looming question when you look at this picture is again a question that has been open for several decades. We know the answer for PRGs and for black box randomization.
Well, this board does not move, right?
Yes.
That's good. Yeah, if you know, that's good.
Good. I'm not aware of the existence of this board until the beginning of the lecture. So the question is, are PRGs necessary for derandomization? Prove that if promise BPP equals promise P, then you get a PRG. Again, and running time that is polynomial, exponential in this case. For other settings of derandomization, we have an answer. For derandomizing proof systems, the analogs of NP, we know that the answer is yes. This was, it dates back to the early 90s by Pagliazzo, Cabanets, and Avi, but it was proved in a much tighter way in the algorithmic method of Fry and Williams. This is part of the proof. And Lijie, I think, is going to talk a lot about this in the next talk. So for proving the randomization of proof systems, the answer is like a resounding yes. For the randomization of BPP, this has been open for several decades and we have no clue. We have conditional results telling us that it's true, but there hasn't been a sliver of progress.
So you want to stress the black box. This says that it never helps you to look at the circuit you are trying to derandomize. I mean, if the answer is yes, if you are given, I mean, everybody knows that, well, I don't know if everybody knows, but you should know that the algorithm, the deterministic algorithm for primality testing, came into the world because they first of all devised a new probabilistic algorithm. One is Aldo and the student, I forget that, maybe Vinay, before the famous result. They designed a new probabilistic algorithm. There were many probabilistic algorithms for primality testing. They designed a new one, which they believed they could derandomize. They believe that the analysis of the way it uses its randomness is one where they can, generate the randomness deterministically. And that's what they did in the famous a.k.a. paper. So it was born by the randomization of an algorithm that you understood. Now you are given an algorithm, another probabilistic algorithm, like for PIT. Maybe you can just look at this and understand what it does with the randomness, derandomize. If the answer there is yes, it says that you never need to look at the algorithm you derandomize. There's one method that does them all, those that exist, or that were not yet invented.
Right, thanks. It also says that the randomization is equivalent to the circuit lower bounds up there. I want to mention two new areas of research. They're quite broad and touch upon the questions that are written here. The first one is called non-black box randomization. And it tries to avoid this question. Instead of proving that PRGs are necessary, we bypass PRGs. And we construct new algorithmic approaches that indeed look at the circuit that we get to de-randomize.
So is there a non-uniform version of that question? And what's not about that?
What do you mean by non-uniform?
So you mentioned that this would imply that de-randomization is equivalent to circuit lower bounds.
Let me write, because I want to write promise BPP equals promise P here and explain later, but just so that I can answer your question, this conjecture says that if this is true, then that is true. And this is equivalent to that.
Oh, okay.
Right? Good. All right, so in non-black box randomization, we completely bypass this. We find new methods, and the advantage here would be twofold. First, you want to get weaker assumptions, right? You don't want to rely on circuit lower bounds. And secondly, you want to understand better. PRGs, we understand them. PRGs are equivalent to these lower bounds. But the randomization is the thing that we actually care about. We want to understand the structural meaning of the randomization. What is it equivalent to? Which problems is it related to? This is the thing we started from, and we don't understand it yet. So I'm going to be very informal here. So I'm going to touch upon this in the third talk, but I'm introducing this mainly as an open question and active area of research. So if we have this kind of PRG, we know that promise BPP equals promise P, and you can show that if promise BPP equals promise P, then you can get these kind of average case PRGs. I'm not explaining how, but you can show it. So this kind of segment sits in between this thing and that thing. And we have a result saying, I'm very informal here, you can compute in polynomial time, but in parallel, like in n squared steps by polynomially many processors, a function that is hard for probabilistic time, say n to the 100, almost all inputs. Because you told me to write large here and large here, so now I have only a small space here.
Write large everywhere.
Okay, so for people listening, I'm going to say this out loud. This is promise BPP equals promise P. And this says that polynomial time in parallel n squared is hard for probabilistic time, say n to the 100, on almost all inputs, which is a new type of lower bound that we will get into in depth in the third talk. Then you get this conclusion. We have a partial converse, but not a full converse. So the intuition here would be that this is a new type of lower bound, but it relates the randomization of machines to showing that deterministic machines can compute a function that is hard for probabilistic machines running in smaller time. This is basically the intuition of what's going on here. And again, it scales. So this is something that I haven't defined. Oh, larger. RP, it's the one-sided error version of PPP, is contained in its exponential time. So C is universal. This is a very mild randomization. And
it's not clear even why it's derandomization. It's the running time of this probabilistic machine on the left can be n to the zillion, even if C is 5. But C is 5. And then.
Right. We don't know how to do such. We don't know how to derandomize probabilistic time n to the zillion in time 2 to the n to the 5. And again, if and only if something like this holds. So this would be X is hard PP. And I'm not defining this. I want to mention this because I want to highlight the following question. Prove an equivalence promise PPP is promise P, and let's call it some structural lower bound. For example, a separation between deterministic machines and probabilistic machines, some kind of lower bound of this type. Let's show an equivalence. Okay. This is one active area of research, and the other that I wanted to talk about. Oh, I didn't mention, of course, such a thing, you want to do it using non-black box techniques, obviously. The other question is something that is called super fast randomization. It was initiated by Doron Moshkovitz, O, and Zuckerman a couple of years ago. And the idea is that if you look at the derandomizations that are written there, even in the top rows, they say something like BPP equals P, which means that for every algorithm running in time t, you can derandomize it in time 2 to the big constant.
T to the big constant.
Yes, sorry, t to the big constant. Thank you. Say probabilistic time t goes to deterministic time t to the million, which isn't very practical. We want to ask what is the actual cost? If I have a probabilistic algorithm running in time t, how quickly can I derandomize it? I'm going to just mention one result. So I didn't mention the middle row over here is a work by Lijie Chen by me, and this is another work by us. And this is under appealing hypothesis. I'm not writing them down since I'm going to prove this in this talk and in the next talk. So we'll see the precise hypothesis. So probabilistic time t contained in deterministic time n times t. So we derandomize with basically a linear overhead, but a multiplicative payment of n, the input length. For a large t, this is very fast. For a small t, this can be even quadratic, say if t is linear. Still, this is a very good randomization. And we can beat that. For every n in dt time t, this is an average case randomization. There exists L prime in d time. Randomization overhead here would be n to the epsilon times t, where you can get epsilon to be as small as you want. So this is basically no overhead at all, such that for every polytime sampleable distribution x, that probability that there is an error is negligible. In other words, the second statement says that you can derandomize without paying any time overhead, just n to the epsilon, such that no machine that runs in polynomial time and tries to find an error succeeds. Again, this polynomial time distribution X is an adversary trying to find an error, and no adversary succeeds. The second question, I didn't mention what are these hypotheses, but they're very strong. So, find sufficient and necessary hypothesis for super fast derandomization.
Only appealing. All you need is necessary.
Okay. A big table, a survey of decades of results, a couple of open problems. Are there any questions at this point? Okay, I think we can take a 5-minute
Sure,
break.
yeah.
Yeah, let's take a 5-minute break and reconvene for the technical part of the talk.
So he can come back with you. I mean, he knows what to do.
The observation that I was making was that, okay, yeah, so as I pointed out, I should have been thinking of like time complexity.
Formalism.
Time bounded. The distribution is
תשאל לו, טעית אותו.
אבל עובדתית אני מוביל. אתה יודע, אין זמן להקל שום דבר.
You said the time bounded conjecture.
לא, ברור שצריך יותר זמן. כל הזמן.
I'm saying
Time bounded conjecture is two problems.
no, but yes, so you know, in the definition of something that is sample, right? Distribution. What happens? The concentration.
ברחוק זה נראה מה זה כאילו, יש פה שאלות מדהימות.
Yeah, exactly. So the same heavily ignores the random part, right? So because now
מה זה הבי?
יש gap, right? These are bounded. Bounded gap.
So single time problems?
yes, exactly. Based on something resembling requiring to fool every sampleable thing, you need to at least do anything that has very function. You need to get the answer right. Complexity because if that doesn't get sample intuitively,
שזה פחות או יותר
Here you were talking about things with feeling.
גם בספר שלך עוד לא הגעתי
if it's.
לא, לא, אחד הספרים הראשונים שלמדתי לפי הספר.
So you have one target.
Being able to be a whatever you're doing, whatever is preparation problem, matches.
Actually, I'm very much confident. You would say this is
Viene legale, ma forse la
not as big. 60 people, I think.
Explicitly find it out. It's very good. Sign of a good definition.
And it's really not.
מה אתה עושה?
I mean, they do.
היום נראה
After the
The good news, the good news is to counteract.
אני אולי אתה רוצה שאני אספר לך משהו?
But you can get around it. It seems that
basically.
Oh no, there's no mistake.
And it seems like it's common to
bad
do
news
two
is not
sections of the
mistake.
same course.
The bad news is that something that conjecture is just flat out false.
יש קוילו ומה דיברו על ספקטור אינדיפנדנס ואנטרופי אינדיפנדנס כאילו משתמשות די חזק ב-high-dimensional expansion. אז מצאתי הוכחה של עמוד אחד מרטיליאלית שחזרת את כל הפריים. שום צורך עכשיו עם הבנו שיש לזה קשר, זה וונזי צ'ן זה זה שעשה את
מה אתה דבר? I think
הבנו שאילו אפשר איכשהו לאחד את הפריימוורק של טיעונים מרטינגליים באמת כאילו עקרונות מפגרים. בקונטקסט הזה, אני לא יכול ללכת חזרה לאלמנט של אז לא חשבתי, אבל זה מחליף את הלוקל טו גלובל. זהו, שיש שם איזה משהו באלגברה לינארית שלא ברור, אתה יודע, כשאתה עולה רמה.
That is done too, right? The 5-year thing. And they kick you out to thank you for your problems.
אני ניסיתי די הרבה למצוא ארגומנטים.
Oh, really?
Okay, let's begin. Okay, but you will get All the understandable parts only. Okay, so in the technical part, which comes now, I'm going to mix two things. I'm going to mix a proof of a new result from last year that mostly uses technical tools and approaches that are old. And it couples them with a couple of new observations. So for people who haven't seen this type of proof before, it will be nice because you are getting like the classical approaches in high level and most of the tools that are used. For people who have seen it before, then you are getting the new observations, and most likely no one will understand. But I will try to do it well.
Everybody will understand.
Good.
We'll make sure of it. But remember, this doesn't move.
Okay. Well, why?
No, because later you may want it. I mean, if this.
No. I'm happy with. Okay. Yeah. I'm not preserving it.
Yeah, it's whatever you don't need later, you can.
Thank you. Okay, there is one paradigm in constructing PRGs. It's the same paradigm. It's a paradigm since 1984. Normally signed is 1984, 86. Then the previous Nissan, the Nissan Vigor song is 88. I want the Nissan for AC0. That's
it's the same year. It's the same week.
There are so many stories. Okay.
Yeah, there are many stories. Right? Whenever you want. Yeah,
but if it's from 1988, you get no credit. It dates back to Sipser from 1986. Okay. And it's called the Reconstruction paradigm. You told me that you got it from there, right? Later. Okay. The Reconstruction paradigm. We start with a hard string F. I'm calling it F because we sometimes think of it as the truth table of a hard function. But I don't know what hard means. I have no clue. Hard is high Kolmogorov complexity, high time-bounded Kolmogorov complexity, high circuit complexity, truth table of a function that's hard for algorithm. I don't know. It's a hard string. I don't even know where I got it from. I got it as an oracle.
Is it a family of strings for increasing n, or is it just a single string?
Well, typically for a PRG is just one uniform machine that works for every input length. But now I'm defining like a uniform transformation that gets as oracle a hard string.
Oh, okay.
The transformation will be uniform, the string will be an oracle, and if like you have hypotheses that allow you to efficiently generate hard strings, then perfect. The PRG will generate the string by itself and then output zero. Okay, so we get this hard string and we transform it. This is basically the PRG. We transform it to a set of pseudo-random strings.
A set of pseudo-random strings, again, it's a distribution on a few strings that look like a distribution on all strings.
So you think of it, what Avi said, the distribution will be over a random seed. And this is G1 to the n with this first seed, G1 to the n with the second seed. So every seed will define one of these, G1 to the n, and the seed here is like 2 to the L, right? Using our notation from before, L was the seed length. And typically these involve tools that you might know. Error correcting codes, algebraic constructions working over fields, projections, set systems. You got the string, and in the end, you'll do some encoding and you'll project it in some way. And the main argument is called the reconstruction argument. So the reconstruction argument says that assume a distinguisher D for the pseudo-random set. Then we construct a procedure for the hard string F. And the point here really is the contrapositive. If the string F is hard, then there is no such procedure, meaning that there does not exist a distinguisher. And I didn't specify what hard is, so I'm not specifying what a procedure is. Typical instantiations take this reconstruction. So this is a reconstruction algorithm that with access to the distinguisher D gets an index Z and outputs like the Z's entry in F. but you can think of many other notions. Okay. And like looking at this, there are two different parts. One part is defining the mapping. The other part is defining the reconstruction. And the real bottleneck is in the reconstruction, because whatever the computational complexity of this thing is, this is the hardness that we need to assume for F. So if a reconstruction is something with high complexity, then we need to assume that F is hard for things with high complexity. And this is why, for example, it was easiest to prove the top row over there. The top row over there talks about hardness for circuits. So the reconstruction would be a non-uniform circuit. It is strong, stronger than the machine. It's relatively easier to prove.
The machine, you mean a program? The machine sounds pretty much like
a Turing machine.
No,
Yeah.
I know.
Oh, so what did I say?
No, Turing machine is fine. What's my machine?
I don't remember.
Machine, yeah, a program. Yeah.
Program, sure, okay. So I think I might have said a mistake because of what Avi said, so I'm just going to repeat it. We want hardness for circuits over there. The reconstruction would be a non-uniform circuit. And it's relatively easy to construct them because they are stronger than Turing machines.
You just have to prove existence.
Right. If we want to start with hardness for uniform algorithms, we need this entire thing to be uniform. So it's a stronger requirement and we need to work harder. This is the entire technical approach. And if we want, okay, what will actually, no, last thing, if we want to get super fast randomization, we need to do this reconstruction without overheads at all. Because if this reconstruction adds a lot of overheads, then we will need to blow up this F so that it will be hard even for these overheads. And if we blow up this F, we blow up everything here and things become slower. So super fast randomization is the randomization without overheads, the reconstruction. Like noticing what is going to be our distinguisher D. Our distinguisher D is going to be a probabilistic machine M with an input X. And the input X could be worst case, could be generated on average, etc. Just something to keep in mind that what we're trying to fool is something like this. All right. No questions about this part, right? So I'm going to prove the following results. This will be basically one proof and end-to-end, which includes a reconstruction argument of a super fast randomization algorithm. And for every epsilon, there exists delta. These two are constants, such that the following holds. So that's non-uniformly secure one-way functions. I'm going to talk about this in a moment. And that for every constant k, there exists a problem in time to the kn, right? So this is slightly above 2 to the n. This is super exponential. And for time 2 to the k minus delta. And you know what, just to make my life easier in a couple of minutes, if you don't mind, let me call this input length L. It's still exponential, I just changed the notation. Now, what I just wrote is trivial. This is time hierarchy. This is unconditionally true, but I am allowing this weak thing over here 2 to the 1 minus delta times L bits of advice.
So I'm not sure this notation is familiar at all.
Oh, okay.
Too many.
So this is,
Flash.
it's like, okay, thank you. So this is a Turing machine that runs in this time, but for every input length L, it gets from the heavens 2 to the something smaller than L bits of advice that is supposed to help the machine compute the hard function. Now, if I would have written 2 to the L here, then this machine could compute anything. With 2 to the L bits, you can give the entire truth table over L bits. And this is near maximal. We are not giving the...
Let's specify the input length for this problem, so maybe it's the function of 2 to the L or L bits.
Input length. L. It's an L bit function. We can compute it in high exponential time. We can't compute it in smaller time, even if we get so much advice that it is almost the entire truth table, but it is not the entire truth table. Look, and I will mention something about this.
So maybe let me say just something about this notation connecting it to circuits. What Roei defined before, size, circuit size T is the same as uniform machines running in time T with a device of length. Basically, what tells the machine, here is the circuit you should use when you are running on inputs of this type.
Exactly.
It's a very convenient.
Also, it is very similar to time-bounded Kolmogorov complexity.
Right. So my plan to describe the hypothesis after I write the statement failed. Describe them now. Good. So Avi talked about this in circuits. Lijie talked about the connection to time-bounded Kolmogorov complexity. I want to mention another thing here. This is a generalization of what we saw before. In the classical results from the 90s, we had that like time 2 to the n is hard for size 2 to the epsilon. You can think of as like, okay, higher time beats smaller time with the device. Here we're just taking this to the maximum. We're taking the advice to be essentially maximal before the result trivializes. We're saying even with near maximal advice, higher time beats smaller time. So this is one hypothesis, which basically generalizes the classical ones from the 90s. The other hypothesis, non-uniformly secure one-way functions, is very standard in crypto. It's not a hypothesis that belongs in the derandomization world, but it's completely standard in other worlds.
But you need it exponential or
No. Polynomial.
Polynomial. The usual. So factoring is hard.
Factoring is hard for it.
Yeah.
I think one function is used in very early generalization work.
Right,
So it's not really, okay, I don't know, yeah.
Yeah, no, true. As Lijie says, like the 1982 papers about randomization started with the great.
Mikal is the originator of hardness implies randomness. In fact, Silvio Micali's thesis is titled Hardness versus Randomness. Oh, he's so.
Yeah. Okay, let's see what we get from these conclusions. We get that probabilistic time n to the c is contained in deterministic time n to the c plus 1, plus some tiny epsilon that you can get to be as small as you want. So it's essentially the derandomization that we saw before, where time t goes to time n times t. This is what's going on here. All right. Any questions or comments about this statement that we will now prove?
Is there a candidate problem where people believe this is true, that like that d time and d time?
And probably take a complete problem for the under linear time reductions for this class. Actually, I don't even know if there's a complete problem when k is fixed.
Yes, right. You just take a fixed Turing machine and you print simulated Turing machine on the rest of the.
On the?
So you take.
Well, oh yeah, you just simulate it for 2 to the k steps without getting k as part of it. So yeah, like complete problems, but they're artificial. They have like a complexity flavor. So it's like getting no response, telling you a complete problem is hard. I don't know any other thing, but Like think of how you prove this statement when there is no advice. These are also weird problems. They're diagonalization. Go over machines, each machine, flip the output. So if I do something stronger, I don't expect to. We have some natural candidates. And I also want to emphasize that the strength here is in two aspects. The first we talked about, this part is getting a lot of advice. The second is that the time gap is very small. It's like 2 to the KL and goes to 2 to the K minus delta. Okay, but it's polynomial in the time bound, so we have such things when advice doesn't exist. Other thoughts, comments, questions? Right. I'm going to do a preliminary step, and then I'm going to draw a high-level picture of it. The preliminary step will be to cheat.
Quite small.
What? Oh. Step 1, reducing the number of random coins to n to the gamma for some time gamma that I can take to be as small as I want. Okay, so we are starting with a machine.
So these are random coins to the BP time machine that
Let's
simulate.
just define it. So proof over here. So let 0 be n to the C time machine. This is the thing that we want to simulate. The first thing that I want to do is, now it's using n to the C coins, I wanted to use n to the gamma coins, where gamma is tiny. So I'm going to use the crypto hypothesis for this. And this is a theorem of Pascal, Vitaliazzo, Levin, Luby. So under the crypto assumption, there exists a PRG. Let's call it 1 over n PRG. G, I want to call it outer, because we're going to compose PRGs in a second. Seed m to the gamma for output length m. Okay, I just denoted it by m. So the seed length will be m to the gamma. M to the gamma prime for whatever prime that you want. For any gamma prime, gamma, and most importantly, running time m to the gamma prime. Circuits, arbitrarily large polynomial size.
This is already in Blamy-Cali and but
Oh, it started from one-way functions.
yeah, so now it starts from one-way.
I thought that like without Hastel, it's a transformation of non-uniform one-way functions to non-uniform PRGs.
You want the uniform. Sorry, good. Yeah, very good. Yeah,
Okay, thank you.
yeah, that's fine.
Okay, and the thing we also put something here that doesn't appear in the original paper, which uses like standard techniques, which gets the runtime.
The assumption is not uniform.
We don't need the edge, right? Because the assumption is non-uniform.
The assumption is security against non-uniform, and the conclusion is security. Yeah?
Yeah.
Okay.
Yeah, it's Blamy-Cali. Yeah.
I didn't know that. Okay, thanks. Four, 52. Never mind. Early 80s.
21, Blamy-Cali.
And the thing that we're using that is slightly non-standard is that the PRG runs in time that is essentially linear. We can get it to run in time m to the 1 plus gamma prime for an arbitrarily small gamma prime. So we're going to do an obvious thing and define m of x sub s equal m0 of x. This PRG with seed length s, sorry, and output length 1 to the n to the c. So the new machine M takes n to the gamma random coins. It fits these random coins to this PRG, the cryptographic one. This thing spits out n to the C coins and simulates the original machine. And this has some tiny overheads, right? Because if the running time increased to be n to the C plus a tiny constant, but I want to ignore all the overheads. I just want to pretend that I now have a machine that uses n to the gamma coins and behaves exactly the same using this hypothesis.
So without the one-way function assumption, what's the best speed one can get?
Well, if you're willing to assume hardness for non-deterministic distinguishers, then you also know how to avoid the hybrid argument. Otherwise, you run into the hybrid argument and then you pay for this thing in the least decodable code. At least.
Okay. Yeah, I think it's eighth.
I think cubic at least, right?
Okay, it's probably eighth, depending on which two.
This is what DMOZ stated, right?
I think STV probably give you eighth.
Still pretty good.
8? Talk to practical people? I don't know. I think they hate 2, right? Okay. So let M be an n to the C time probabilistic machine using n to the gamma coins. Fantastic. We used the crypto hypothesis, we cheated, we reduced the number of coins to be n to the gamma.
Wait, just a question about the previous thing. If I give you the function, you can use it as a black box to build the PRG, or is it?
Yeah, it's a black box transformation.
Okay.
Again, this is cheating. What I really want is a linear time computable PRG with n to the gamma C. It happens to be the case that crypto stuff knows how to give such a thing. But I could have just assumed that there exists a linear time computable PRG with C length n to the gamma, which is weaker than this crypto assumption.
The statement you see there is the first result that signify that maybe randomness is not too hard. Everybody was using one-way function for crypto and said that you can derandomize BPP by just 2 to the n to the gamma time instead of 2 to the n time. This is sort of amazing. Let's go.
I want to emphasize that one thing that is easy, but not like, I don't think it dates back to there, like they knew it, but they didn't use it. Like the runtime is linear here. It's not polynomial.
Yeah, no, even before this addition, just that's the first time where people started suspecting that maybe randomness is not all that hard.
Okay, so now this will be the big proof sketch. It is going to stay with us, so it is on the moving board. So we have a machine M. This is the machine. I draw it as a triangle. Its running time, I want like a visuals of everything. It has a big running time. The running time is n to the C. And we are equipping M with advice. The advice is the worst case input that it uses to try and break the PRG that we are going to construct. So this is an input X. It is of length n, which is significantly smaller than n to the C. So for the visuals, C can be here, okay? No, really, this is important. So if I have to erase things, I will erase them. This is n to the C, it is very big, this is n. We are going to take the truth table of the hard function and 2 to the L bits. Something like n to the 1 plus epsilon.
So you should write problem, you should call it F in the theorem.
Thank you. Right, this is F, the hard problem. We instantiated on L bits, where L is something like 1 plus epsilon log L. Okay, so the hardness is kind of slightly larger than the input, but it is much smaller than the run. And now the first thing that we are going to do, we are going to use an error correcting code to encode the truth table of F into a new truth table, which is just the encoding of F. I'm going to denote it by n bar. And this is 2 to the L bar, which is again n to the 1 plus O of epsilon. With even, even smaller instead. It's epsilon 1 plus gamma. Gamma is arbitrarily small. So it will be an encoding with a very good rate. Right? It doesn't add a lot. The truth table stays of size approximately the same, slightly larger than L. And intuitively, the role of the encoding here is to ensure that if there is a procedure that can compute this hard string on slightly more than half of the entries, this is a corrupted code word, then this procedure can be transformed without too much of an overhead to a procedure that computes this thing on all entries, the good code word. This is why we use the encoding.
Complexity theory, this is called worst case to average case reduction. If you can compute the error corrected version on average, then you can compute the effect.
Now we're going to take a set system. I'm going to write some sets here. There will be overall n to the 1 plus O of epsilon sets. And each set will be of size n to the gamma. Each pseudo-random string will be the projections of this encoding to the corresponding set in the set system. So we have a set here of size n to the gamma. We just project, and we get a string of length n to the gamma. We have n to the 1 plus epsilon such sets. So we get a pseudo-random set of n to the 1 plus epsilon strings. The R set n to the 1. This was one part of the construction, the generator. We need to show that it can be computed quickly. The other part of the argument is reconstruction. We're going to take this machine n with the input x, and we're going to transform it to a procedure that computes f sub L. This is f with L bits in this complexity. And when I say this, I mean this over here. And to see what's going on, we said that the hard function is this thing, and we want to take k that is approximately c. So let me write it down. Like we need to define what exactly hardness we use. So the hardness would be, where can I write it? Hardness that is approximately c. So time 2 to the KL is something like n to the c. But if we slightly decrease it, we get the complexity of this thing. Maybe I should write it in a more organized way. The runtime n to the c, which is approximately 2 to the k minus delta times L. By a choice of L and k, if we are taking k that is approximately c, by a choice of k and L, this thing is smaller than n to the c. So we took L to be slightly larger than log n. Actually, that's all I wanted to say. Questions? Because I see that these messy parameters were confusing.
So what relation do we want between epsilon and delta?
Oh, epsilon is the target overhead in the derandomization. You're taking delta to be sufficiently small in the hardness hypothesis to support this epsilon.
Will be a fixed constant factor, right?
Yeah, it's a linear overhead.
Delta will be an epsilon over 10 or 100.
Yeah, exactly. I think, no, maybe there's a square there.
There's not, yeah. Okay.
Not sure. Do you remember?
It depends on this. I think it depends on overhead in the design, which can generate in a very, very like.
The weak designs. Do we get a square root there? Okay. Anyway, I'm not sure. Maybe there's a square there.
Oh, I think the square probably comes from the error correcting code.
Yeah, that's what I thought. It's from the Reed-Muller that you get a square root, but I don't think it matters. Right. Okay, we engineered the parameters. Let me put it another way that maybe will be less confusing. We took this to be slightly larger than n. And we engineered the parameters such that the running time of the machine M would match the hardness over there. It would be slightly less than 2 to the KL. A reconstruction algorithm is going to run n. So a reconstruction algorithm is going to run in time n to the c. And we want to make sure that this is still like below the hardness that we had for f. This is the reason for the choice of parameters.
Before parameters, it's not clear. I mean, I think it's intuitively clear to most people why applying error correcting code will make relate worst case to worst case complexity. It probably is very unclear for people who didn't see it. Why just projecting on some subsets will give something that is a set of pseudo-randoms.
True. Like I'm going to do a full proof.
What?
I'm going to do a full proof.
Yeah, I know, but I mean, before parameters, that's another mysterious.
In high level, what is going to happen in the reconstruction? The reconstruction is this machine that runs in time n to the c, and it has n bits of non-uniform advice with x. It will be a distinguisher for this thing. We will then transform it to something that computes this on average, again with advice. The advice would be sufficiently small so as not to violate this hardness hypothesis. So it is still something that runs in time n to the c with advice that is less than maximal. And then using the properties of the code, we'll transform it to something that computes this thing exactly, again without too much of complexity overheads. So the final complexity will be dominated by the running time of M and by the non-uniform advice provided by X, which are precisely, the advice is slightly smaller than this string, and the running time is slightly smaller than the hardness hypothesis over there. This is the high-level plan.
Sorry, so I may have missed the exact details of that final step where you take the error correcting code and then transform it into a set of pseudo-random strings. Did you say exactly what that step is, or will you say it in detail?
Yeah, I will say it in soon. But I said like in high level what's going on. There's a set system and you're using projections according to the sets. All right, let's do it formally and slowly. Actually, now I'm going to say a lot of things that are relatively standard because I'm instantiating standard classical tools. So one thing for people who already know these tools, the observation to take here is that the observation that we already did is that the distinguisher, the one we are working against, is a uniform machine with access to n bits of advice. It's not an arbitrary circuit. We can quantify and limit the advice that the machine gets. And when we separate the running time and the advice, we are able to get this kind of super fast randomization results. This will make sense to you, I think, if you have seen this before. If not, then now come all the technical details. All right. So the error correcting code, we are going to use the concatenation of Reed, Muller, and Adamard, which gives you this thing. The theorem, Sudan, Travis, and Han. So there exists code mapping 2 to the L bits, 2 to the L bar bits. L bar is 1 plus O of gamma L, so great rate, and it works in near linear time. Such that the following holds. For every truth table F tilde. F tilde is a corrupted code word that agrees with the real code word on half plus gamma. Sorry, half plus 2 to the minus gamma times L of the indices. There exists an oracle circuit. Call it DEC, because that's the decoder, of size that is relatively small compared to the parameters that we care about. It will be 2 to the O of gamma times L. This is relatively small, such that when the decoder gets oracle access to the corrupted code word, it computes the hard function. And the real theorem is even stronger, but we just need this simpler corollary of it. So that, okay, for every corrupted code word, we can take a small circuit DEC. This is small, it will not affect our parameters, such that when DEC, the decoder, gets oracle access to the corrupted code word, it precisely computes the hard function.
Again, for people who never saw this, this is what's called local decoding. It's the decoding, unlike standard error corrected code, you don't want to recover the entire code well, but for every index, for every entry of a bit of the code, you want to get it. It's local, with the big field.
Typical results even make this effective. Like it's not that just that there exists an oracle circuit, you can output a list of circuits and one of them is guaranteed to work with this F, but we're not using it right now. All right, so now it suffices to compute F plus 2 to the minus gamma times L of this. If we can do this with low complexity, then we can compute all of F with low complexity. And now comes an observation, again, from the 80s. This is due to Yao, which says the following intuitively. Like, assume that there is a distinguisher that distinguishes a bit chosen at random from this truth table from a uniform bit. So this distinguisher, you're giving it like to distribution F, something uniform on L bits, and you're giving it a uniform bit. And let's, for simplicity, also give it a prefix. So this is prefix of size R. And this algorithm sees this distribution and sees this distribution and distinguishes between them. Let's say for simplicity that the algorithm screams yes more when it sees this thing than when it sees this thing. Well, this is basically equivalent to computing F on average. Because like almost syntactically, when you see this thing, you're able to recognize that this is the value of the function, which allows you to compute it on average just by, guessing and seeing if the distinguisher screamed, yes, this is the right value. So good. This would allow us to take this truth table and output one bit of pseudo-randomness from it. Fantastic. Just by choosing a random bit in the truth table. Now we want n to the gamma bits. So the first attempt that we are going to do, let's choose n to the gamma bits at random. Okay. Of course, this is too much, right? Like we are not able to afford seed length n to the gamma, not even close. So what are we going to do? And this is the idea of Avi and Noam Nissan. Let's still be in high level. We want to choose the set. I don't want to be confused with there. So we want to choose. Yeah, the fact that I wrote this sentence will be very confusing. We want to choose coordinates of 0, 1 to the L let's call them y1 up to y into the gamma, and ideally they would be independent and we would be happy and we will finish. But we are choosing them such that we are controlling for dependencies. And I'm going to define this precisely in a second. Typically, in classical instantiations, they will be almost independent. We will choose them such that the correlation is very small. Here, the extreme parameter setting that we will see in a second, you can't really say that they're not almost independent, they're extremely correlated. But still, we will be controlling for the dependencies, which will allow us to reduce to the case of distinguishing one bit from uniform, which by Yau's observation will allow us to compute the Hart function. And this is the plan.
Maybe you want to, this y1 to y and to the gamma is, you should think of it as like one output of the generator. One of the strings, right? One of the two to the whatever strings.
So the random string. Exactly. Right. Okay. I'm going to erase this coding theorem because I really want to present. Oh no, I have this thing in the bottom. Okay. So we're going to use a construction that is slightly improved by Reingold and Bathan. It's
probably better if you erase the error correction so that people see
the right-hand side. Okay.
Everybody believes, or I thought they would have asked that it's part of this error correction code you're done with.
Let's see how much time do I have. So I know what content. Oh, I have 10 minutes. All right. We're going to see the construction at least. So there exists an algorithm that gets input 2 to the L bar and then to the gamma. It runs in time to the L bar times N to the O of gamma. So look at this running time. For us, it's small. It's again almost linear. It prints the following set system. This is another set system than that one. It prints sets S1 up to Sn to the gamma, which are contained in 1 plus O of epsilon times L bar. So these are subsets of this universe. This universe is slightly larger than L bar, such that each set is of size L bar. So good, each set will be able to specify a location for us. We'll soon see how. And we want to say that the pairwise intersections are small. Like every two sets, Si and Sj don't intersect too much. And we will do this using slightly weird notions, right? We say that the average intersection is small. Okay, no problem. We want to bound the average intersection. And we actually want to bound its exponent. But fine, the intuitive notion here is that take the log inside. What you're really talking about is that the average intersection is small. So it will be smaller than 2 to the 1 minus 2 epsilon times L. And this is these are weak designs by Reingold and Bathan. This is not complicated. This is just a probabilistic construction with the method of conditional exploitation. It works. And the construction of the PRG is the following. So take a random seed S. This random seed is of length 1 plus O of epsilon times L. We want for like this fixed value of the seed to give us many locations in the truth table of F bar. So we look at like the set S1, assume that this is the set S1. This set has precisely L bar bits. So this set specifies one position in the truth table, let's say over here. If I look at this set over here, let's call it S2, you can see that they intersect a lot. But we have a bound on the intersection. It can't be complete. So again, S2 defines another location over here, and so on and so forth. We have S n to the gamma, we have n to the gamma sets. So each fixed value of the seed defines n to the gamma locations. This would be one set here. And given a seed, we will simply project. So let me write this formally. So this is the Nissan-Wigderson generator. This is our generator G, with access to the hard string F and seed X. Take F 1. This in a second. To F. So what's going on here? We took the seed S, we projected the seed S to each of the subsets of length L bar. We evaluated F on them. And here note that I use notation like F with parentheses, as if F were a function, not a string. I don't care, it's the same. This is just the relevant index. So for each seed, we are getting n to the gamma pseudo-random bits. And the seed length is 1 plus O of epsilon times L bar. I want to do a quick sketch of the complexity. This is it. This is the generator. We finished describing it. Now, before talking about its complexity, let's just leave a moment for questions.
So if the sets were independent sets, were chosen independently, then these values will be independent and this will be a random string. Now they are not independent because there are inputs that share a lot of bits, but hopefully not too much, and they look independent enough.
Okay, so if this is the first time you're saying it, think of these as like locations that intersect, but not too much. If this is not the first time you're saying it, there is something new that is hiding. Because now I want to bound the complexity of this generator. So I'm looking at everything here. And notice that I'm not counting the complexity of the generator as the complexity of taking one seed and outputting one pseudo-random seed. I'm counting a batch computation. The complexity of just taking F and outputting all of these strings together. And this is the right notion. There is no reason to count each of these strings separately. And indeed, using this batch computation, we can do this efficiently. So what does efficiently mean? Okay, so the first step is actually the most costly one. The first step is computing the hard function F. How much does it cost? Well, F has something like n to the 1 plus epsilon bits, right? This is what we chose, slightly larger than n. And each bit costs something like 2 to the k L. This is the fact complexity. So this is something like n to the c plus 1 plus epsilon. As computing the hard string took us this time, and this is already maxes out everything that we are allowed to pay. The randomization time will be this. So the first step was already the most costly. Computing the error correcting code, we're just doing it once for the entire batch of strings, no problem. And computing this transformation, since this thing, constructing the set system, is done only once, it's not costly. So the costly step was to do this. These transformations were cheap. And now comes the final step, which we tend to forget, which is to evaluate M on the pseudo-random set. See how it behaves on the pseudo-random strings. And the number of strings that we have is n to the 1 plus O of epsilon. And the running time of M is n to the c. So the time here would be n to the 1 plus c plus O of epsilon. Okay, clearly we are not going to have another half an hour to finish the proof because we have something like 3 minutes. The proof is a reconstruction algorithm that takes this M and this X and works out the steps in reverse that we said before. First, uses the fact that this is a distinguisher to get a distinguisher for a single bit here of the pseudo-random generator, distinguishes a single bit from uniform. Then it uses the properties of the set system to instantiate this. It uses the properties of the set system to instantiate this distinguisher and control for the dependencies. Sorry that I can't be more specific.
But at least you can relate the intersection size to the delta which appears in the hardness assumption.
True.
So it has to be related, I mean, somehow that.
Yeah, but I have to explain the partial
Yeah,
truth.
not to explain, but just to point out that.
Essentially, this is the amount of advice that we are going to pay. Like we controlled for the intersections such that 2 to the intersection would be something like this. And this is the advice that the algorithm would get when moving from a distinguisher here to something that computes this on average. But we carefully crafted the parameters such that this thing would be slightly less than n. So the advice again would be dominated by x, by the worst case input. This is the reason for the entire choice of parameters. And in each step of the reconstruction, the most dominant part of the advice would be x, and the most dominant part of the running time would be that of n, which is n to the c. And the real reason what's going on here is that there are n bits of non-uniform advice that we cannot get around if we want to do worst case derandomization. So we kind of have to take a truth table that is slightly larger and work out everything so that like in the entire reconstruction argument, we will never exceed this n.
You're also using advice to guess the input on which M is a distinguisher?
Yes, precisely. Exactly. Like this is the bottleneck. Like we start with the M and with the worst case input, so it already has n bits of advice, right? Now that it has n bits of advice, I don't mind like getting the advice here to be, slightly less than n, which is nearly maximal over here. Backing away for a second, what happened here is an end-to-end reconstruction argument. I just omitted its details. The reconstruction tools that we used, codes, this set system with Wick designs, the Nissan Vickerson generator, come essentially from the 80s, 90s, and very early 2000s. The tools are old. The new observations that we had here are that we can separate the advice and the running time, that we could use a small truth table, that we can batch compute this entire thing, and that we can take this hypothesis, namely setting things up, instantiating the old tools in a way that allows us to get Derandomization with only a multiplicative overhead of n. Right, I think that's it for now, right? Thank you very much.
More questions?
What about much smaller overheads? Is there anything known about what you can or can't do with much less than that?
Okay, so this is the overhead that we get under reasonable assumptions. And you can show that under a hypothesis called sharp n-set, I'll mention it in a minute, but under sharp n-set, this is optimal. You can't do any better. And sharp n-set is like an exponential separation between sharp p and n. Okay, like there's a function in sharp p that non-deterministic exponential time cannot compute. By exponential time, I mean like, 2 to the 0.99n, like 2 to the n minus a tiny bit, right? However, okay, so this kind of settles it, right? Like you have to pay this and you pay this. I mentioned the result earlier, and we're going to say it in 2 weeks, that if we are willing to settle on derandomization that is not correct on worst case, but that no polynomial time observer can find a mistake, which is effectively worst case because no one can find a mistake, even though they exist, they're unreachable. then you can get something like this. M to the epsilon times t, for an arbitrarily small epsilon. And this requires non-black box techniques. You can't do it without non-black box techniques, and we'll show how to say it with non-black box techniques.
So could you say again, what's the difference between the?
That's on average.
Yeah, this is like a effect. No polytype thing. Find an error with non-negligible probability.
Actually, what I meant is, do you have any much weaker assumptions that will tell you that you can't do it, for example, with only constant over or something like this?
It's a good question. It's a good question.
Stronger assumption?
No, I mean, like you said, that, for example, sharp NCF shows that you can't get overhead of n, but I'm wondering if I just want to not get a constant overhead.
It's a very good question.
I guess you can relax the n size to be something like 2 to the 0.501, and then get something non-trivial.
You think? I don't say it immediately, but I take your word if you say it.
I think so, because essentially you have the 2 to the n by 2 time Merlin-Arthur algorithm,
right? And
you want to show like some non-trivial generalization is impossible.
So you need like an n set for time 2 to the n over 2, not 2 to the 0.05. Oh, you said 2.5.
That's
yeah, 2 to the n over 2. Yeah, Lijie's answer is great. If instead of like taking time 2 to the n basically over here, you take 2 to the n over 2, you can rule it out.
And does the bottom one have any negative results?
I mean, what can you hope for more? Like this is 2 to the n to the little of 1.
I meant under n.
Sorry?
I meant under some other assumption that you can't.
But there is almost no overhead at all here. You are trying to rule out an overhead of log. Like working with logs and machines is already like.
Well, a constant or log.
Like you are trying to rule out something like this, right?
Yeah, for example.
Yeah, that was our question.
So I think we can get, actually we can, yeah, that's true, I'm sorry. I think we can get something like this, under stronger assumptions, but so this is an upper bound, conditional one under very strong assumptions, but I don't know like about constant here. It's plausible that you can get it, but
I think that's an issue about the error probability at the beginning, because at the end you want to some negligible error probability.
Right.
So if you start with some randomized algorithm with already negligible error probability, then maybe you can get very fast generalization. But otherwise, you need to pay some cost in the error reduction at the beginning.
Well, you can get an average case derandomization where you replace non-negligible with 1 over polylog. Comes from the one-way function.
But you cannot expect to not to have a log appearing there just because machines are simulating other machines.
The log's fine.
So unless you use a different model of computation like this, or Uspensky machines or something.
I mean, it's not about expecting, it's about proving.
Yeah, the assumptions that we get for this, let alone the assumptions, you know what, forget. The assumptions for this are very strong. We don't know if they're true. They're not like the assumptions that we got here are strong, but they're kind of a form that you recognize, right? The assumptions here are of a new form. So it's not like I'm saying this upper bound and I'm kind of convinced it's true.
More questions? Thanks.
Thank you.